Welcome to Homework Lib.
For this question, we're asked to use the graph, which is figure P2.62, to describe the acceleration as a function of time, or the graph describes the acceleration as a function of a time of a stone that starts at rest and rolls down a hill. And we're asked to find the velocity after 2.5 and 7.5 seconds. So the first thing we need to do is find an expression for the velocity. Okay, so I'm going to use the fact that looking at this graph, I picked two different times, and you can find the slope of this graph by using rise over run as a common way of finding slope of a straight line. So I picked two different times. The first time I picked at T2, which was 8 seconds, and the acceleration at that point, A2, is 8 centimeters per second squared. At time T0, we have an acceleration of A1 of 2 centimeters per second squared. So the rise over run value, which would be the change or d squared of the velocity by dt, right? The reason this is true is because d squared by dt squared is equal to the change in a, d sub a, by dt, right? So the change in acceleration with respect to time, that's our slope. But acceleration is the change in velocity dv dt. So the change in acceleration with respect to time is d squared v dt squared. And we're going to let this equal some value. And we're going to call that value c, okay? But what is the change in acceleration with respect to time? Well, it's simply the rise over run, or the slope. So this is going to be a2 minus a1 divided by t2 minus t1. So the reason I'm doing this is because I'm going to develop an equation for the velocity from this information. So if I plug those values in, I find that c is equal to 0.75 centimeters per second cubed. Okay, well, now I'm going to try to get back to acceleration. And to do that, I'm going to integrate the d squared v by dt squared. So if I integrate, I end up with dv by dt. And that's going to be equal to the integral of c with respect to time. Well, this simply gives me c times time plus some integration constant c1. Well, how do we figure out that integration constant? An easy way to figure out that integration constant would be to plug in the time t equals 0 into our expression. At t equals 0, we know that the acceleration, or dv dt, is equal to 2. Well, the only way that's possible, if you plug that into this expression, because c times t would be 0, because t is 0, that means c1 would have to equal 2 centimeters per second. So we know from just plugging in those values that c1 is 2 centimeters per second from our initial conditions of t0 equaling 2 centimeters per second squared, or excuse me, 2 centimeters per second squared, because it's acceleration. So now that we know that, we can integrate once again to get an expression for velocity. So the velocity will be the integral of c times t plus c1, all integrated with respect to time, dt. So if we do this integral, we find that this is equal to c times t squared over 2 plus c1 times t, and then we're going to have another integration constant c2. But again, at t equals 0, the velocity is 0, and that's only true if c2 is equal to 0, because if you added a c2 term onto this and you plug t2 into our expression, then we have c times 0 squared plus c1 times 0, so those are all equal to 0. So essentially we have c2 is equal to whatever the velocity is at time t equals 0, but the velocity at time t equals 0 is 0 because the stone starts at rest, so that means c2 is 0. So now we have, and I'll go to the next page here, now we have an expression for our velocity. We have velocity is equal to c times t squared over 2 plus c1. And we know what c is. We know that's 0.75 centimeters per second cubed. We know c1 is 2 centimeters per second. So we have everything we need to find the velocity, or it's c1 times t, excuse me, c1 times t. So we know we now have everything that we would need to find the velocity, right? Okay, so now we just plug in our values that we're asked to find the velocity for. The first one is at t equals 2.5 seconds. So we plug 2.5 seconds into our expression, and we find that the velocity here is equal to 7.34 centimeters per second. We can box that in as our solution for t equals 2.5 seconds. And the other one was at t equals 7.5 seconds. So we plug 7.5 seconds into our expression for velocity, and we find that the velocity there is equal to 36.1 centimeters per second. And we can box that in as our final solution for part A. And in part B, we're asked to graph the velocity as a function of time. Okay, so here's our axes. This is time in seconds. This is velocity in centimeters per second. It starts out at 0. I'll graph it in red. It starts out at 0, and it increases as a rate of t squared plus t, right? So it's not increasing linearly. It's increasing as a squared function, so it looks something more like this. And we can plug in some values. For instance, we know that at 2.5 seconds, so we'll say 2.5 seconds is around here, we're at a value of a little bit more than 7 seconds. So 7 seconds would be about here. Or excuse me, 7 centimeters per second. And then at a value of about 7.5, we'll say this is about here, we know that we're sitting at a value of closer to 36. So that would be somewhere up here. And that would be our solution for part B.